Hi everyone, my name is Ioannis, and today I'll be presenting our work, FirmSolo, which is a system that exposes binary Linux-based IoT kernel modules to dynamic analysis. So I assume that everyone here either knows or at some point has interacted with an IoT device, like for example, a smart thermostat. What's cool about IoT is that it's constantly evolving to the point that in the future, we might find it in advanced robotic systems or even spaceships designed for planetary destruction. I just hope that this technology does not inherit the same bugs as current IoT, because then it'll meet the same fate as in the movies. So yeah, even though IoT has been with us for a while now, it still remains vulnerable to security attacks. In the past, we've seen critical security incidents involving IoT devices happening, like for example, the Mirai botnet attack in 2016. Nowadays, we see dozens of IoT bugs that are considered dangerous continuously popping up throughout the years. So if you thought that your IoT devices are safe, well, that's not the case. Fortunately, the research community has focused on analyzing the firmware that runs on these devices. However, most of the systems designed primarily focus on only one aspect of IoT firmware, and that is its user-level aspect. Specifically, when it comes to Linux-based IoT firmware, the most popular techniques are rehosting techniques. Unfortunately, since these techniques depend on emulators that lack support for the majority of the IoT hardware out there, they cannot emulate or analyze the firmware binary kernels that run on these devices. But what if we had other parts of the IoT kernel code that are very interesting and potentially easier to analyze, like the binary kernels? And I'm referring to the Linux loadable kernel modules within IoT firmware. However, before doing that, we need to first solve a very important problem similarly to the IoT kernels. What if we have these IoT modules only available in binary form? This is a very frequent phenomenon in the IoT domain. However, we're very interested in analyzing these kernel modules because we know they contain vulnerabilities. Like, for example, the memory corruption vulnerability affecting the NetUSB kernel module, which raised some awareness when it was first found. So the question remains, what do we need to analyze these IoT modules? Well, we actually need custom kernels that are supported by emulators to dynamically load these IoT modules and then analyze them. So how hard can that be? When I first started working on this project, the first thing I tried is to load a random IoT module in a random kernel. And immediately I saw that the kernel complained that the version between the kernel and the kernel module was not the same. Then I addressed this challenge and tried again, only immediately to find that the external symbols, which are functions and data structures required by the IoT modules to load into the kernel, need to be provided either by the core kernel itself or by other modules that have to be loaded first. I addressed this challenge and tried again, but this time I came across a kernel module crash. And that is because the memory layout of data structures that are common between the kernel and the kernel modules has to be consistent. If that doesn't happen, then we might have misaligned data structure accesses happening during emulation, which might lead to kernel module crashes. So in summary, what do we need? We need to match the version between the kernel and the kernel modules. We need to make sure that the symbols used by the kernel modules are available to them. And we need to make sure that the layout of data structures that are common between the kernel and the kernel modules is consistent. So our framework, FirmSolo, is designed exactly to address these key challenges and expose the IoT kernel modules to dynamic analysis at scale. FirmSolo is a three-stage analysis approach, and given a target firmware image, it will first run the information gathering stage, which will extract metadata about the IoT kernel of the target firmware. Then the second stage, called K.C.R.E, will use that metadata to compile a custom kernel that can load the IoT modules of the target firmware. And lastly, in the downstream analysis stage, FirmSolo will use examples of dynamic analysis systems to analyze these IoT modules. So let's delve a little bit more into each stage. Starting with the information gathering stage, FirmSolo will statically analyze the IoT kernel modules of the target firmware and also the IoT kernel, if that is available. and will extract important metadata information, like, for example, the endiness of the architecture of the target system, and most importantly, the symbols required by the kernel modules to load into the kernel, and also the version of the IoT kernel. Now, before going further, let's revisit a little bit the challenges that FirmSolo has to address. I'm not going to mention the first challenge of matching the version between the kernel and the kernel modules, because that is trivially addressed by the information gathering stage. When it comes to making symbols available to kernel modules, like in this example, the NF register hook, what FirmSolo needs to do is to essentially find the corresponding configuration option that guards the implementation of that symbol within the kernel source code. In this example, that option is the config net filter, and then enable that option during the kernel build process in order to make that symbol available in the final kernel binary. If someone wanted to do that manually, then they would have to use Linux's menu config facility and then toggle the corresponding option themselves. Now, regarding the layout of data structures, let's visit another example, that of struct.net, which is used to define network namespaces in the Linux kernel. And let's say that we have a random IoT module that tries to access the gen member of struct.net at offset hex 324 from the base address of struct.net. Now, in order to make sure that the layout of struct.net is consistent between the kernel and the IoT module, FirmSolo has to compile its custom kernel with the config IPv6 option enabled. If that doesn't happen, then the gen member will be placed at a different offset, and then when the IoT module tries to access that member, it will instead incorrectly access an arbitrary memory address. And if that happens, kernel module crash might happen. So the second stage of FirmSolo, called K.C.R.E, is designed to address these two key challenges. K.C.R.E is responsible for reverse engineering the IoT kernel of the target firmware, and based on the information gained, compile a custom kernel that is able to load the IoT modules of the target firmware. K.C.R.E consists of further three steps. The first step is the KFS kernel build step, where FirmSolo will build its custom kernel. But first, in order to do that, it has to reconstruct approximately the configuration of the IoT kernel for the target firmware. Specifically, what happens is that FirmSolo feeds the metadata extracted in the previous stage to a static analysis process that will produce a kernel configuration file, or a .config as it's called. That configuration file contains the configuration options that have to be enabled during the kernel build process in order to make all the symbols required by the IoT modules, like, for example, the NF register hook, available in the final kernel binary. Then FirmSolo will choose the correct toolchain for the target firmware, and will use the .config file along with the source code of the open source version of the IoT kernel to compile its custom kernel, which we call KFS. The next step of K.C.R.E is the firmware emulation step, where FirmSolo will emulate the custom KFS kernel and try to load the IoT kernel modules to find which of these can actually successfully load into that kernel. For more details, refer to the paper. The third and final step of K.C.R.E is the DSLC step, which is responsible for addressing kernel module crashes that are related to misaligned data structure accesses, like the struct.net example that I mentioned previously. The purpose of this step is to reintroduce the offending kernel modules back into the analysis pipeline. But in order to do that, FirmSolo needs to find which configuration options have to be either added or removed from its custom kernel's configuration in order to fix the layout of the offending data structure. I'm not going to go into much detail about how this step actually works. All I'm going to say is that FirmSolo leverages the fact that some of these crashing IoT modules have an open source variant that was compiled along with the KFS kernel in the kernel build step. Then FirmSolo statically analyzes the IoT module that crashed and its open source variant, and gathers important information like the type of the offending data structure, the member that was incorrectly accessed, the incorrect offset where that member is located at, and the correct offset where that member should actually place at. And given this information, FirmSolo will find the configuration options that have to be added or removed during the kernel build step in order to align the layout of structnet in this case. And then we'll rerun the whole K.C.R.E stage from the beginning. Now, finally, in the downstream analysis stage, we use examples of existing dynamic analysis systems to analyze the IoT modules in our dataset. In this case, we use the Tri4CFL kernel fuzzer to fuzz the kernel modules through their ioctal interface, and also the Firmadyne dynamic analysis system to confirm the bugs found by Tri4CFL and also test against known exploits from the exploit database. However, here I have to mention that other dynamic analysis systems could be integrated into FirmSolo to analyze these IoT modules. So we evaluated FirmSolo on around 57,000 IoT kernel modules, and FirmSolo was actually able to load 64% of them, while prior work actually cannot load any IoT modules. With Tri4CFL, we fuzzed a small subset of the IoT modules in our dataset through their ioctal interface, and we found 19 previously unknown bugs, which we, of course, reported to the affected vendors. We also confirmed some of these bugs on a physical IoT device, which was very cool. So in summary, I presented our framework FirmSolo, which builds custom Linux kernels that can load binary IoT kernel modules and then expose these kernel modules to dynamic analysis. You can find our source code available using this link, and also you can contact me using my email if you have any further questions. Thank you.